Myself, Rajiv Basakov, student of Namsi Government College Physics Department, stand here to deliver my short topic assignment given by our respected sir, Dr. C.P. Khatiwada, under a Sikkim University Physics Paper 6 Sessional B, which consists of 25 marks. And my topic is Maxwell equation and Poynting theorem. Maxwell equation. So Maxwell equation consists of sets of four equations. The sets of four equations that describes the behavior of electric and magnetic field and how they relate to each other. So Maxwell equation in integral form. There are four equations. The most form which we used is Maxwell equation in differential form. Now look a closer look to the every equations of Maxwell's. The first equation is Maxwell's Gauss law. So the first equation is a Gauss law, basically a Gauss law. So Gauss law is the first Maxwell equation which dictates how the electric field behave around a electric charge. Gauss law can be written in the terms of electric flux density and electrical charge density as del dot D is equal to sigma V, rho V, where del is equal to, here del is our Nebula operator and D is a displacement current and rho is a charge density. So second law is Gauss law for magnetism. So basically this law, what's the physical meaning of this law is that monopole doesn't exist. So there is no monopoles. So the divergence of the flux density D equals to the volume of electrical charge density. The divergence of the magnetic flux density is 0. Let's see how it becomes 0. So possibly the divergence of B is 0. To support this statement, the field do not flow in or out of any volume, they flow circularly. So there is a no divergence. That's why a divergence of B is always 0. The third law is Faraday's law of induction. So del cross E is equal to minus del V divided by del T. It states that whenever magnetic flux linked with a circuit change, then induced electromotive force EMF is set up in the circuit. This induced EMF lasts so long as the change in magnetic flux continues. The magnitude of the induced EMF is equal to the rate of the change of magnetic flux linked with the circuit. And this is known as Faraday's laws of induction. And the last law is Ampere's law. So del cross H is equal to J was the Ampere's law, but there was some contradiction in Ampere's law because it was violating the continuity law. To correct that problem, Maxwell has introduced a term del D by del T. So when the term was introduced, the contradiction was solved and it was a great contribute. And among the four laws of Maxwell, Maxwell had only worked on Ampere's law and give the modification to Ampere's law. And that modification changed the entire modern physics. So the Ampere-Maxwell equations is del cross H is equal to del D by del T plus J. It relates the electric current and magnetic flux. It describes the magnetic field that result from the transmitter wire or a loop in electromagnetic survey. For steady current, it is a key for describing the magnetometric resistivity experiment. Let's see the application of Maxwell equations. Wherever we have an electromagnetic device, then we must remember Maxwell equation. So application of Maxwell equations. So antennas used to receive the electromagnetic signal. On that also we use a Maxwell equation. In transmission lines, the ceiling fan capacitor work on the displacement current, which is introduced by a Maxwell. The MRI scanners used in hospitals, magnetic tapes, and also used in electricity generation. So Poynting vector and Poynting theorem. Let's look at what is Poynting vector and Poynting theorem. When an electromagnetic wave travels in space, it carries energy, and energy's density is always associated with electric field and magnetic field. As it is associated with electric field and magnetic field, the Poynting vector represented as S, or which can be also represented as P. So P or S is equal to E cross H. So what is a Poynting vector? Let's see. The rate of energy travel through a per unit area, that is the amount of energy flowing through per unit area in a perpendicular direction to the incident energy per unit time, is called Poynting vector. Now look, what is a Poynting theorem? Before that, let's see the unit of Poynting vector. The unit of Poynting vector is watt meter inverse square. So Poynting theorem states that net power flowing out of the given volume V is equal to the time rate of degrees of stored electromagnetic energy in that volume decreased by the conduction loss. That is the total energy leaving the volume, which is equal to rate of degrees of stored electromagnetic energy minus ohmic power dissipated due to the motion of charge. And here is our Poynting theorem equations. Now we will see the interpretation of this equation. So interpretation of Poynting theorem, the left hand side term, that integration E cross H dot ds. What does it represent? It represents the rate of outward flow of energy from a volume S. And the right hand side, the first term, minus del by del t u h square divided by 2 plus epsilon naught E square divided by 2 dV, represent the energy stored in electric and magnetic field respectively, and their sum denotes the total energy stored in electromagnetic field. So total terms gives the rate of degrees of energy stored in volume V due to the electric and magnetic field. In right hand side, there is also a second term called integration E dot J dV, and this gives the rate of energy transfer into the electromagnetic field. This is also known as work energy theorem. This is also called as energy conservation law in electromagnetism. And here we end our topic Maxwell equation and Poynting theorem. Thank you. Have a nice day.